Hello everyone, I am Soroor, PhD student at the University of Ottawa, and I'm joining you today from Ottawa. I've been an intern at Vector Institute since September 2024, working with the Applied AI Design and Delivery team. Today, I'll be sharing a project I worked on in Green AI Bootcamp, a collaborative effort focused on optimizing large language models for efficiency and sustainability. Here's a quick overview of today's presentation. I'll start with the problem of the growing carbon footprint of AI. Then I'll walk through key strategies and optimization techniques for reducing the emissions of large language models, followed by how we explored these ideas in practice during the Green AI Bootcamp. And finally, I'll share highlights from our research contribution that was recently accepted at the IEEE conference on AI. AI's growing carbon footprint is becoming a major concern. As models scale up, so does their environmental impact. Their carbon footprint is increasing at an alarming rate. And this isn't just a technical issue anymore, it's becoming a broader environmental and societal one. Training GPT-3 is estimated to have produced over 550 metric tons of CO2. That is roughly equivalent to 125 gasoline-powered cars running for a year. And it's not just for training. The ongoing cost of inference, especially at scales, adds significantly to that footprint. Estimates suggest that the training process for GPT-4 may have resulted in emissions between 12 to 14,000 metric tons of CO2 equivalent. To reduce the carbon footprint of LLM, there are key approaches. These are the areas of focus and topics of exploration in Green AI Bootcamp. First, measuring energy usage and carbon footprint through tools like Hot Carbon and Sentinel's Deep View enable measurement and monitoring of energy consumption during LLM training and inference. Also, exploring small models and architectures offers promising alternatives to larger-scale LLMs, maintaining strong performance while requiring fewer resources. Third is model compression techniques such as knowledge distillation, quantization, and pruning, which can reduce model size, lower inference latency, and minimize computational costs, all without significant loss in performance. For local inference, using frameworks like Ollama enables running LLMs directly on local hardware, reducing both latency and carbon emissions. This also improves data privacy by eliminating the need for cloud-based processing. Also, parameter-efficient fine-tuning like LoRa allows adapting large models to specific tasks by adapting only a small subset of parameters, significantly lowering training time and compute needs. Efficient LLM alignment is also a promising approach. Reward-guided generation aligns model outputs with human preferences. Once trained, a reward model can guide multiple tasks, often replacing the need for repeated fine-tuning and saving energy. Here is 3 LLM optimization techniques that introduced in this program, as a part of this program. Pruning, quantization, and knowledge distillation. Pruning efficiently removes redundant model weights without sacrificing accuracy, and the advantages are accelerated inference, memory efficiency, and energy saving. And trade-offs might be removing too many weights, or critical ones can degrade model accuracy. Quantization lowers numerical precision to enhance computational efficiency, and it can reduce memory usage, faster inference, and energy efficiency. And it might slightly reduce the accuracy depending on the model and task. For the knowledge distillation method, it creates smaller, faster models with guidance from larger ones. And the advantage is model comparison, knowledge transfer, and efficiency, and the potential trade-off might be a slight drop in accuracy. Gains depend on hardware support for integer operations. After this brief overview on efficient LLMs, here I will give a bit of a context about the Green AI project and how we approached it as a team. The Green AI Bootcamp was a collaborative initiative led by industry innovation and AI engineering teams and the support of TAs and guest speakers. And special thanks to Michael and Tahniat, my mentors and direct managers in this project. The bootcamp officially kicked off in October 2024, but I joined earlier right from the ideation phase. And during this phase, I took initiative to dive into recent research on sustainability in LLMs and data centers. And that exploration helped us for brainstorming sessions and contributed to shaping the scope of what we wanted to explore. As the bootcamp progressed, we had 3 learn days designed for knowledge sharing and hands-on experimentation. I presented 2 sessions during this time. One was the opening presentation on the environmental impact of generative AI, where we explored the growing carbon emissions of recent AI models, and the second was a hands-on workshop on deploying LLMs locally, showing how models can run efficiently on edge devices. Throughout the project, I led some of the regular one-on-one meetings with the sponsors. Many of them were deeply engaged and curious about the topic. Some came with their existing use cases, like improving the efficiency of their internal Q&A chatbot, while others wanted to explore as many optimization techniques as possible to take that knowledge back into their organizations. During our build days, we supported sponsors in testing a range of optimization techniques. The DeepSeek model was released during the bootcamp. It reinforced the idea that LLMs still have significant potential for efficiency improvements. A couple of teams also were interested in exploring the DeepSeek model. And finally, on Showcase Day, all the teams presented their work. Some teams shared their findings, and one had a live demo as well. Some interesting insights from participant teams are one team developed the lightweight AI assistant for investment analysis. It could interpret financial data and ESG rating while running efficiently in a lightweight environment, a strong example of balancing utility and sustainability. Another project focused on identifying sanctioned entities from complex unstructured text. By fine-tuning a smaller model, the team not only improved accuracy, but also cut emissions compared to larger setups. And the third one is a chatbot project aimed at internal support, showed that with thoughtful optimization, it's possible to reduce emissions without maintaining or even improving the performance. It was a clear example of how green AI can enhance both cost and customer experience. And one group tackled the challenge of document analysis in a regulatory compliance. By optimizing memory usage and inference strategies, they made it possible to handle lengthy legal content efficiently without adding unnecessary carbon costs. As a part of this project, I had the opportunity to co-author a research paper that was recently accepted at IEEE Conference on AI. I'd like to give a special thanks to my collaborators, Tahniat, Sedaf, and Shaina. In this paper, we explored a case study and present a practical framework that shows how we can significantly reduce the carbon footprint of large language models without sacrificing the performance. The proposed framework tackles energy efficiency in LLM deployment through 3 interconnected components: local inference optimization, the selection of energy-efficient LLMs, and a comprehensive evaluation methodology. For local inference, we use Olema to run LLMs on edge devices. Our main optimization technique was quantization, and the task of the case study was sentiment analysis. And we made sure to include carbon footprint measurements as a part of our evaluation, not just model accuracy or latency. And the results. After applying quantization technique, we observed up to 45% reduction in entry usage and carbon emissions. That shows green AI isn't just a nice to have, it's achievable right now with the right techniques and approaches. That wraps up my presentation, and happy to take any questions you may have.
Oh, great. So the local inference optimization, which you presented in the last slide, can you explain a bit in detail on what, how you did that? Like, was it using Olama or?
Sure. Yeah. The local inference in the paper, do you mean?
Yeah. This
Uh,
is using quantization. Okay.
exactly. We use the LLM, the Olama for this one, and it is easily running on any like system that you have. So it's on your device, and even you don't need to have an internet connection. So it's easy to use, and we use Olama. Yeah.
Okay. Thank you.